So let's do the law of reflection. So he imagined that all of light's rays go like this. I'm going to try to draw this, to try to draw them as parallel as possible. So according to Huygens, there are wave fronts in here that go forward in time, like this. So the blue are the wave fronts that are propagating forward, and the black lines that I have are the actual direction of propagation of light. So if I call these different points A, B, C, D, E, F, G, H, I. So A, B, C, D, E, F, and G, H, I are the wave fronts that are moving forward. So there's nothing in the way right now. So I can say that the time it takes for rays to go TA to G is the same time that it takes B to H, is the same time as it takes from C to I. And since light travels with the speed of light, can I also say that the time it takes from C to F is the same as the time it takes from F to I? There is no reflecting surface, nothing. Is that statement true? Okay. If I make a surface in the middle, oh, this is going to be a problem. I didn't draw this carefully. Will I be able to move this? Possibly. So I want you to draw a line through DI. And I want you to rename this as J. This point. And then can I say, if there is no reflecting surface, may I also say the time that it takes ray BE to go EJ plus time that it takes JH. There's no reflecting surface. Okay, now I want you to put the reflecting surface in. So now imagine that this is the reflecting surface. Now we are introducing reflecting surface. What will happen to these rays? These will be reflected back. So I'm going to try to draw these. So from point D, let me see if I can draw this carefully. So imagine that this is what happens. Then from my point I, will I also have wave fronts that go like this? Going backwards, correct? Is this angle 90 degrees?
Yeah.
Is this angle also going to be 90 degrees?
Yes.
And that one. All of these angles have to be 90 degrees, correct? Okay, so if I take this part and I zoom in, can I call this distance? Let me say if I call this was my F, I'm going to get rid of that. I'm going to say this was F. I'm going to rename this as M for now, this point. And then can I call this N, M, N, and this is still I.
Yeah.
Okay, so I'm concentrating on this triangle. If I call this angle gamma, then normal to my new surface, I call this angle theta I. May I call this new angle, this angle right here, the one I colored in, I'm going to call this angle alpha, and I'm going to call this angle beta. This angle is alpha, this is beta, that is gamma. And I'm going to call this angle my theta reflected. Okay, just pay attention. So imagine, I'm going to redraw this so it's not that confusing, but I'm going to try. This is gamma. So I'm redrawing this part. So that's D. This is theta I. This is theta R. This angle I've just drawn, I've called this alpha. And this angle that I've just drawn, I've called this beta. Okay, so I'm just redrawing that part. Okay, zooming out. So I've just drawn the one in the green here. Okay, so now, do I know that to be true? Gamma is the same as beta. From geometry?
Yes.
These are the same angles on the two lines. That's going to be true. Okay, so in my triangle, is alpha the same as gamma?
Yes.
Yes? Is alpha the same as gamma?
Yeah, it is. Yeah.
Oh, yeah. Okay.
This can only be true if theta I equals theta R. Or if that doesn't make sense, can I also show you another way? So do you know for a fact that this is 90 degrees? Do you know for a fact that this is 90 degrees? So can you also write gamma plus theta I is 90 degrees? And can you also write alpha plus theta R is 90 degrees? We said that gamma was the same as beta. So can I rewrite this as theta I plus gamma equals 90 degrees? And theta I plus gamma equals 90 degrees. So that means theta I is gamma, no, 90 minus gamma, correct?
Yes.
90 minus gamma. And theta, oh, sorry, this should be R. This was my fault. Trying to go too fast. This is theta R. That is also 90 minus gamma. What do these two equations imply to you? That must be true. So there's two ways you've disproved that. Woohoo!